Okay, we have our first setup experiment ready to go. We're going to change the force every trial, but we're going to keep the mass exactly the same. So you'll see here's the carriage, and there's a whole bunch of washers inside, and there's a string attached to this carriage that goes down this air track, and then it goes over the pulley, and it comes down to these washers on the edge, two washers on the edge. So the way to keep the mass the same the entire time will be to take two washers out of the carriage every time and put them on the end. Because the thing that's accelerating is the carriage, the string, and the thing on the end. So that whole thing is one object, and the mass will remain constant, but we can just put part of the mass in part of the object to the other part of the object. So we're going to put mass on the end of the string here, and so that'll increase our force, pulling it down, but the entire mass of the whole thing will then remain the same. So every single trial, we're going to take two washers out, and we're going to put it on the end, and we're going to measure the acceleration rate every single time. Okay, so in the first part of the experiment, we're going to put the carriage that has 12 washers in it and two washers on the end. We're going to put this entire thing on the scale to see what the entire mass is. Looks like it's almost 142 grams, 141.9 grams. Okay, so we're going to do part one of the air track inquiry. And if you watched the video, the first thing we did was put the whole thing, the carriage and the washers on the end, all on the scale together to figure out the total mass. And that total mass was like 141.9 grams. We're going to call that, we're going to convert that to kilograms to be 0.142 kilograms. And we're going to put that here because it's constant mass. We're not going to change that ever. The mass is going to stay the same throughout the whole experiment. So that'll be important, and that'll what we'll be checking later to see if we get that. Also in part one, our force is going to change by two washers every time. So I'm going to put two washers on here. And we'll see that it's 9.2 grams. You need to convert that to kilograms, take it times 9.81, and that'll be the weight that we're going to add on to the end. Every trial, we're going to add two more washers onto the end. We're going to take two washers out of the carriage and put them on the end. That will increase the force, but it will not change the mass because the total mass of the washers on the end and the washers in the carriage will always remain the same if we take them out of the carriage and put them on the end. So you need to convert this to force before we go on. Okay, so the forces, there were two washers on the end of the string, and when you saw watching the video, we put those two washers on the scale, and they were 9.2 grams. So if we divide that by 1,000, that's 0.0092 kilograms. And we take that times 9.81, we'll get the force of two washers in newtons, and it was 0.0903 newtons. So that is going to be, that's our first force. So I'm in this force box here, I'm going to put 0.0903 return. And every time we're going to take two washers out of the carriage and put them on the end of the string. So that will change the force, downward force, but it will not change the mass. The mass will still stay constant because the carriage and the washers on the end are all one object that are accelerating. So I want to add 0.0903 every single time for these 5 trials. So the way I'm going to do that is I'm going to do equals, and then I'm going to click this cell, which is just always going to be the previous cell. And then I'm going to do plus. And then I'm going to click this cell again. But what I want to do is I want to always reference that cell. So I'm going to put dollar signs in front of the C and in front of the 4. Technically, I only need it in front of the number here because when I drag this down, it's going to increment the number. And I always want it to be from the 4th row. But it's always safe. Put dollar signs in front of both of them. So what that's going to do is it's going to take this first cell and it's going to add it to itself. So now I've added 0.0903 onto this. So I can take this now and I can drag this down, and you'll see what it did. So like this, if I click on this one, it'll say C7, which is this one right before, and add to it C4, which is this. So that adds on 0.0903 every single time, so that'll work. Okay, so those are our 5 forces that we're changing, and we want to see what did that do to the acceleration when we increase the force on a constant mass. What did that do to the acceleration? So you should watch the video, and you should record all 5 accelerations from each of those, and then come back and finish this spreadsheet. 2 washers on the end, trial 1. Four washers on the end. Six washers on the end. Eight washers on the end. Ten washers on the end. Okay, so what we want to do is we want to graph these two, and we want to graph them in such a way that the slope will get a straight line, and the slope will be the mass. Because what we're doing here is we are trying to validate, we're going to do 2 different experiments. We're going to try to validate Newton's second law, which is F equals ma. Now this is a nice easy equation because it already fits very well into our straight line equation y equals mx. In fact, the m for slope is in the same spot as the m for the mass. So in this first graph, what would I graph on the y and what would I graph on the x so that I would get a straight line and the slope would actually be 0.142, or the constant mass that we have right here. And you can probably see that I'm going to graph force on the y, and I'm going to graph acceleration on the x, and then my slope should be the mass. So that's why I have it set up here. I have A is in the first column, that's x, and F is in the second column, that's y. So really this is pretty easy. I can just highlight all that. I can insert a chart, and I get a scattered chart, and it says force versus acceleration. Everything came out right. If it didn't, you might have to, sometimes you have to click use column B as labels. If you see 2 different lines of dots, you have to do that sometimes. This came out okay though. So I'm going to go to customize. I'm going to go to the series. I'm going to put a trend line through it. And if I just show the R squared value real quick, it's 0.998, so it's pretty linear. In the label, I'm going to use an equation. And you'll see what I get is the force, or y, equals m times x, and x is acceleration. So right there, 0.153 is the slope of that line. So it's supposed to be 0.142. I got 0.153 as the mass. So you can do a percent error between those two. Subtract them and divide by 0.142 because that's what it actually was. And I'd say that's pretty good. That might be around 7% error or so. So anything under 10% error, I'm fine with. That's awesome. Okay, so it's very linear, F equals ma, and that predicted kind of the mass that we got. And so that is the end of experiment 1, where we tried to validate Newton's second law, and I think we did a good job on that first one. And then in the next video, we'll in this experiment we kept the mass constant. In the next experiment, we're going to keep the force constant and change the mass each time. So we'll see how that works. Okay, for the experiment 2, we're going to keep the force constant this time, the force constant, and we're going to change the mass every time. So the carriage here has 10 lead squares in it, and we're going to remove 2 lead squares every single time. And remember last time we removed 2 washers, but we put them over on the end, and that way the mass stayed the same the whole time and the force increased. This time we're going to take the 2 lead squares out and we're just going to put them on the table. So the mass overall is going to get less every single time, and the force is going to remain the same with 10 washers on the end every single time. So we're going to keep the force constant, and we're going to change the mass this time. The force is on the end, and we're never going to change that, so we're going to use these 10 washers on the end. And so that 10 washers in the clip is 46.5 grams. Convert that to kilograms, take it times 9.81, and that'll be our constant force that we're going to keep all the time. Okay, for part 2, we're going to keep the force the same, but we're going to change the mass every time. So we'll go ahead and find the mass of the entire system again. We have the carriage. We have 10 lead squares in the carriage. We got 10 washers on the end. That's going to provide our force. And we get the total mass. Total mass is 225.5 grams. Total mass. Okay. What we're going to do to change things is we're going to actually change the mass, and that means we're going to take out 2 lead squares. So I'm going to take out 2 lead squares and put them on the scale, and you can write down what the mass of 2 lead squares is. So it's 20.5 grams. And we're going to make a little assumption here. We're going to make an assumption that every single lead square has the exact same mass. So every time you'll subtract off 20.5 grams from the mass of the whole system each time. So we're just going to assume they all have the same mass. So that'll probably work out. Okay, so every single trial subtract off 20.5 grams off of the total mass. Okay, this is the second part of the inquiry. In this one, we're going to keep the force constant all the time. We had 10 washers on the end of the string. We have a whole bunch of lead squares in the carriage, and we're going to change the mass each time by taking 2 lead squares out. So if you watch the video, you'll see we put the 10 washers, or we put the 10 washers on the scale, and that was a mass of 46.5 grams. And if you take 46.5 and you divide by 1,000, you're going to get 0.0465 kilograms. And if you take that times 9.81, then you get a total force of 0.456 newtons. 0.456 newtons. That was our total force, and that's what we're on this end of the screen, and that's what we're going to keep constant. So I'm going to put 0.456 newtons in for that spot right there. Okay. So our total mass, we put everything on the scale, and the total mass to begin with was 225.5 grams, or 0.2255 kilograms. Now, we also put 2 lead squares on the scale, and that was 20.5 grams, or 0.0205 kilograms. And we're going to subtract that every single time, because we're going to take 2 lead squares out every single time. So the way I'm going to do that, let Google do that for me, is I'm going to do equals, and I'm going to take the previous cell, and I'm just going to do minus 0.0205, hit return, and I can go ahead and just drag that down. Okay, let's fix our decimals here a little bit. Oh, there we go. Okay, so those are masses. Our mass decreased. So we took 2 out every time, and what did that do to our acceleration if our mass decreased? And you should watch the video, and you should find those 5 accelerations after we took 2 lead squares out every single time. 10 lead squares in the carriage. Eight lead squares in the carriage. Six lead squares in the carriage. Four lead squares in the carriage. And finally, 2 lead squares in the carriage. We want to graph, prove Newton's second law again, and we want to graph it so that the force is the slope. This is what we kept constant, so we want the force to stay as the slope. So how would we do that? So if we look at Newton's second law, F equals ma, we want the force to be in the slope spot. So what we have is we have y equals mx, and we want the force to be right here in the slope spot. So how would we do that? Okay, so what we could do is we could take, we could divide both sides here by m, and that would give you a equals f over m, okay? And you could rewrite that as a equals f times 1 over m. And that's what we need, because that is like a y equals an m and an x. So our acceleration is going to be our y-axis. We want acceleration on our y-axis. That's this column here. And in our x-axis, we actually want 1 over the mass. We want 1 over the mass. So that's why I left this column in here. I can do a 1 divided by mass column right here. So I'm going to do equals 1 divided by, and I'm going to grab the mass, hit return. And then I can just drag that down. And there's all the 1 over masses. Don't quite need as many decimal places. Okay, so now here's my x and here's my y. And so now I can graph that, insert a chart, and customize, and series. What's the trend line? Let's see our squared value look like. 0.997. It's pretty linear again. And we're going to do the equation. And this right here, 0.448, is the slope. And that's what should be equal to our constant force. And that's not bad. 0.448. We got 0.456. So you should subtract the 2 and divide by 0.456 and get a percent error again on that. That should be, I'm just going to do that real quick. I'm really curious. 0.456 minus 0.448. Okay, and I'm going to divide that by 0.456 times 100, and we get a 1.8%. Wow, that's really, really good. Okay, all right, so in these two parts, one time we kept the mass constant, the second time we kept the force constant, and both times we proved F equals ma with the y equals mx equation, and figured out what the slope should be that we kept constant. So hopefully that helps you understand a little bit more about how we use graphs to validate physics laws.